Today, myself and Damiano are going to talk to you about something called control plane machine sets. It's a new feature in OpenShift 4.12. And in a single sentence, they allow you to replace the infrastructure of your control plane within an OpenShift cluster in an automated way. So to do that, I'm going to give you a little bit of background. I'm not sure if everyone in here has used Machine API before, so let's go a little bit into what that is. Then we'll talk about why this was actually a problem and why we built this new feature. We're going to talk a little bit about how we make sure that etcd doesn't get broken while we're doing the control plane replacement. And then Damiano is going to take us on a deep dive of the features of the control plane machine set. So before we do that, quickly, I'm Joel. I'm the team lead for the OpenShift cluster infrastructure team. We're responsible for Machine API, cluster autoscaler, cloud controller managers, and a whole bunch of other stuff as well. I also have a personal interest in API design and the tooling around that. So if you want to talk about cell validational stuff, I know David's talking next, but that's something I'm interested in as well. Dan?
Hey everyone, I'm Damiano. I'm a software engineer on the OpenShift cluster infrastructure team. I also do Machine API, cluster API, and I'm passionate about Linux, Go, and Kubernetes.
Cool. So a little bit of background then. So if you haven't seen Machine API before, it's basically a Kubernetes declarative way of declaring the infrastructure for the worker machines and the control plane machines in your cluster. We typically have this as 3 individual control plane machines, which then relate to 3 servers in the cloud or on your vSphere or whatever you have. And then we have something called a machine set, which creates a number of identical worker machines. And then those worker machines each relate, again, to 1 server in the cloud. If we take the machine set and go with an analogy that the machine set is kind of like a replica set, then the replica set creates multiple identical pods. The machine set creates multiple identical machines. And those machines are then like pods. So looking at this, the control plane machines have no management on top of them. And so that's like having unmanaged pods in your cluster, which I'm sure most of you try to avoid. Moving on, the control plane, we have this, the control plane is based on 3 machines. There's a certain capacity that gives us. We have nodes and then workloads all trying to talk to the API server. etcd is then on there as well, and there's a certain amount of traffic. As you grow your cluster, that traffic is going to increase, and so the amount of capacity needed by the control plane gets bigger and bigger. In OpenShift, we only support a 3-node control plane, and so the only way to make that bigger is to vertically scale your machines. You have to give it more CPU and more memory. Now, how do you do that? Well, if you look at the OpenShift product docs from 4.11, this is how it tells you to do it, and that's just 1 machine. So that is a very involved process that took me 6 pages to work out, this is 1 machine, I've got to do this 3 times, and if I get any of this wrong, bye-bye cluster. So not ideal. As we're, OpenShift, we've got new services like Rosa and ARO, we're trying to manage more and more of these automatically. We don't want our SREs doing this manually 3 times every time they want to grow the cluster. So we had to make some way to automate this. So how do we do that? Well, we broke the project down into 3 phases, and we introduced 3 different features. One is machine lifecycle hooks, which allow you to inject different actions as you're deleting the machines. We then taught the etcd quorum operator how to use this feature to protect itself and make sure etcd is never disrupted. And then we built control plane machine sets to manage the machine layer. Looking at machine lifecycle hooks, very briefly, you can either block the machine API from draining the node, or you can block it from terminating. This might allow you to do something like, I have storage on here, I want to make sure that's removed before I get rid of the instance in the cloud. I can go and do that with an additional controller, remove my hook, and then machine API will carry on. We taught the etcd operator to use the pre-drain hook. So imagine your etcd cluster, you've got 3 voting members there on 3 different machines. And we put the protection in as those dots around the machines. If I delete one of those machines, nothing happens. etcd is blocking anything from happening there by using that protection. So what do I need to do to get this back to a healthy cluster? Bring in a new machine. The etcd operator will add a new learner member. The learner member will look at the existing cluster, sync up the data, and eventually be ready to promote. When it's ready to be promoted, etcd operator adds the protection, promotes it to a voting member, and then quickly removes the old member from the machine that's going away. Now, if we look at the etcd cluster here, we don't need that machine anymore. We remove the protection, machine API gets rid of it, and we're back to our healthy cluster. So with this protection mechanism in place, it now means that replacing the control plane machines is just a case of deleting and creating machines at the right time. And that's where control plane machine set comes in.
So as Joe was saying, we have introduced these two extensions to OpenShift for the etcd protection mechanism and for the machine deletion hooks. But actually, we needed to add a new component crafted from zero that would be responsible to reconcile the control plane machines. So we created this new operator called the control plane machine set operator, which is similar to other OpenShift operators that you can find in clusters. It's an operator that is responsible for watching a resource, which we call control plane machine set, or CPMS. You will hear me say that. And the CPMS resource is the gateway to for users to configure the control plane machines. So we watch this resource with the operator. The operator also observes control plane machines. It observes them and determines whether they need an update or not. It does a diff between what is contained in the CPMS resource and what is in the provider spec of the machines. And if it finds a diff, then it considers those machines to be updated, and what it does, it starts replacing them accordingly. We have various ways to provide replacement procedures, and we call them strategies, and we will see those, what those are later. So we mentioned we have this resource. This is what users normally should care about, the control plane machine sets, or CPMS. It's a custom resource in Kubernetes. It's a CRD instance, and it mainly contains three important fields. So it contains the desired configuration field, which is numbered 1 down there, is the provider spec. In there we have like details specific to the machine we want to create for the control plane. For example, I don't know, instance size, disk, or other things that we might want to tune at the provider level. So this will be different according to different providers you use. Then we have the strategy field, which we will talk about later. You can set it to 2 different values. And then we have the failure domains. And with the failure domains, you can configure where machines can land. And then the operator will make sure machines for the control plane are spread across these failure domains, right? So, for example, you have failure domain A, B, and C. We want to have 1 machine per each failure domain. We don't want to cram them all on one zone because that's not good practice for high availability, right? So let's look at the update strategy. So we have 2 of them. The rolling update is the default strategy. We created it so that it doesn't require user action for performing upgrades. The user is only responsible to tune the values they want in the field of the CPMS. And then what happens is the operator performs a rolling update. And it does so by behaving similarly to what happens with deployments. Like deployments have the rolling update strategy, and they have like max surge. With this one, we have max surge set to 1, and we're going to perform a 1-to-1 replacement of each machine through the safety mechanism that Joe was explaining. So then that's fully automated and fully safe. We have, oh yeah, forgot. We have, on the left-hand side here, we have an example on how that works. We have 3 up-to-date machines in black up there, index 0, index 1, and index 2. Machines are taking the role of filling in for an index. So in this case, we have 3 of them. They are up to date. What happens is the user then changes the CPMS spec, the control plane machine set spec. The machines immediately go red, which means they are out of date. So the role of the operator now is to go in and replace those machines to match what is contained in the spec. So how that is done is the operator goes in, creates a replacement for the first index. We can see that in black down here in the 3rd line. And when that happens, when the machine is then up and ready and provisioned, we can start deleting the out-of-date machine for that specific index. So we created for index 0. We are going to delete the old one for index 0. So that is the gray one there. So what's going to happen is once the safety requirements are satisfied, meaning that the etcd protection mechanism is happy, the machine deletion hooks are satisfied, we are able to drain the old machine. The new one will take over the etcd membership, and that way we will be able to fully replace it and remove it. So then it's now removed. Index 0 is up to date now, and then we are going to repeat that for 2 times for the other 2 indexes. Again, this is not something the user will need to do. This is fully automated. You can observe your operator do the thing. We can look at it later in a demo. This is the update strategy for onDelete. OnDelete is a bit more of a manual strategy. It's a more user-controlled kind of update. And this way, you can basically observe the machines go out of date and then manually issue a deletion, and then the operator will create a replacement for you. And you will need to do this 3 times for all the machines. Last thing we want to talk about regarding the CPMS is failure domains. Failure domains are provider-specific or platform-specific in this case. For example, in here we have an AWS example. What is going to be in that field is the number of failure domains you want for your control plane machines. For example, AWS has 3 AZs, 3 availability zones in US East 1, let's say. So we have Zone A, Zone B, and Zone C. If we define those on our CPMS, when we activate it, it will basically go in and replace the machines and put them in the various availability zones. This is going to be stable by index, so your index will always stay on that availability zone. And we have a feature called automatic rebalancing, and this feature allows us to say, okay, if a cluster has 2 control plane machines in zone A, 0 in B, and 1 in C, we want to move that extra A machine to B. And what happens is this is automatically done for us by the operator that does this rebalancing. Okay, now that we saw the features that the CPMS contains, how do we get that? So to get it, you can check the compatibility matrix that Joe will show you later. You can see if your OCP or OpenShift version and your platform are a supported configuration. If they are, you can upgrade your cluster to a supported configuration. The CPMS will be disabled. You can enable it. Of course, you need to review what you're doing because that's important. Otherwise, you break your cluster. And there you get your CPMS. The other option is to do a fresh install on a configured specific version that already supports it. And I'll hand over to Joe for that.
So in terms of support, as I said, this feature was introduced in 4.12, initially only for AWS for fresh installs, but for Azure and AWS, you can activate it, and it will be generated for you. For 4.13, when that's available, we also introduced full support for Azure and GCP, and in future versions, we're going to have support for more of these as well. So I know OpenStack are working on that at the moment, and I've got a conversation with the vSphere team to talk about this next week. So we've got other platforms joining, but at the moment, the big 3, AWS, Azure, GCP, are the main supported platforms. And that's kind of all we've got for you. If you want to know anything more about this, then I've got a bunch of links on the slide deck which will be shared. And Dan and I are going to be around for the rest of the day. So if you have any questions, come find us and have a chat. Thanks.